Students, we're going to talk a little bit more about origami, specifically the 45-45 triangle that comes out of that origami folding. So we start with a square piece of paper, and since it's square, it has 4 90-degree angles. And when you fold it in diagonally, then, because these two sides are both equal, these two angles are both equal, they have to both be 45. So 45, 45, and 90. Because we know the total in the triangle is 180. Now, why this is interesting is when you do this again, you get another 45, 45, 90 triangle. And we know that for 2 reasons. This top angle is 45 and it's matching on top of this other angle. So since it matches up perfectly, we know that they are both 45. That's not a geometric proof, but that's a visual way to say those are right on top of each other. They're the same. And when we do that again, if these are 45 and 45, when I fold it on top, it's 45 again. And pull it up here so we get a nice crisp fold. And there's your 90 down the corner again. 45, 45, 90. And do it again. So this shows up all the time in construction because squares are very useful in construction for square tiles and all kinds of stuff. And so a lot of times you'll split a square tile into a perfect triangle. So when you're tiling bathrooms, kitchens, all kinds of stuff like that, ceilings, floors, tiles tend to have 45s and 90s a lot. And there's other triangles that are very common, but this is very, 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 very common. So because squares are very useful. So take a look at that. There's a very, very tiny one. Now the whole idea here, as we mentioned in the other video, was this triangle is similar to this triangle because they're both 45, 45, 90. Is similar to this triangle because they're 45, 45, 90. Is similar to this triangle, which is similar to the bigger triangle, which is similar. So what do we have here? Of course, we have a whole bunch of triangles. That much is obvious. But what it is this little triangle in here, yes, it's a 45, 45, 90, and so is every other little triangle. Those are all congruent. Okay? But if we copy a second triangle down here, take a look at that. If I rotate it this way, again, we have a 45, 45, 90. And this continues. If I copy this one, then now we got, this is the 90, and that's a 45, 45, 90. Okay, so if you can see that. And going further, let's see which other triangles can I extend. That whole triangle right there is also a 45, 90, 45, 90. So if we went all the way across, so any two triangles you connect, you're going to get a 45, 45, 90. That's similar. This bigger triangle right here is similar. That's the 90, the 45, the 45. So all these triangles in here, any sets of 45, 45, 90s, they're all going to be similar. All right. There's one other thing that we want to talk about, though. Let me fold this back down again. In half. In half. In half. Let's get tight folds here. Opposite crease. There we go. That's the way we did it before. Okay. So in half and in half. Now, let's take this little triangle here. Let's start in my corner of my paper here. And let's say this side was 1 and 1. It's a right triangle, so the Pythagorean Theorem is true. A squared plus b squared equals c squared. So we'll call that side C. And again, in a right triangle, it's leg, leg, and hypotenuse. The long side is called the hypotenuse. So for us, it's 1 squared plus 1 squared equals c squared. So that's 1 plus 1 equals c squared. So c is not 2. C squared is 2. So what you have to do is square root both sides, and square rooting the squared cancels, and you just get c the square root of 2. Okay. Got that? Check this out. As we expand it, let's go down here. Let's trace this roughly. Just move down. As I expand it, this side was square root of 2, right? But if I unfold it, that leg that was square root of 2 is now over here. Sorry, the hypotenuse is over here now. And the hypotenuse is now a leg. because this is now the 90. So let me go ahead and trace this now, just real roughly. Whoops. Try to trace a little bit there. We have square root of 2, square root of 2, and now this is the hypotenuse. Again, over here, that was the hypotenuse. Now we're facing a different way. So that's important. It's still the same, similar, not same triangle, but it's still a similar triangle, 45, 45, 90. It's just that it's facing a different direction. So that's kind of important. Now, square root of 2, square root of 2. The Pythagorean theorem always holds for right triangles. Square root of 2 squared plus square root of 2 squared equals 2 squared. This squared plus this squared equals that squared. Now, square root squared, those cancel. That's just 2. Square root squared, canceled. That's just 2. So, oh, wow, c is 4. No. C squared is 4. So, again, we got a square root, and you get 2. Okay. So, the math's not too hard, but if I try and do it in my head, I make mistakes. I forget the square root or, this or that. Something goes wrong somewhere here or there. But it ends up being a nice whole number here again. Now, a couple things here. Take a look at this. This is the Pythagorean theorem. Pythagoras is famous for this. He did a lot of other things. He started a school and stuff like that. Supposedly, according to the legends, he was obsessed with numbers and he absolutely hated this fact. This is not an easy number to compute. This is not an easy number to express as a fraction. In fact, you can't. So they didn't actually like those types of numbers, even though he came up with this theorem. For us, it gives us these numbers a lot, and it's very, very important in all kinds of ways. But yeah, he didn't like those irrational numbers, those square roots. So they were weird numbers. They're hard to actually, write out. We have calculators nowadays, though, so that's how we handle them, among other ways. But we'll get into it. The nice thing for us mathematically is square root and square cancel each other. So we just play around with the algebra, and it comes out with a whole number. So we end up with this pattern of you had a whole number before and then a square root. Now we have 2 square roots and a whole number. Now when we unfold this, again, this was square root 2. Now when we unfold that, whoops. Alright. So square root 2, and then the base side was 2. Let me move this up here. So the same triangle from before. Square root 2, and then the base was 2. When we unfold it, now it's 2, 2, and we can see this. This was square root of 2, and there's 2 of them, square root of 2, square root of 2, so that's a total of 2 square roots of 2. Alright. So let's see if that's, if you're okay with that. That's a square root of 2 and a square root of 2, so it's 2 of them. It's 2 square roots of 2. Kind of like this was x and x, it'd be 2x. So these square roots, don't worry about them too much. They operate the same way. Alright, now take a look at that. I'm going to move on to the new page because I'm running out of room here. So we had 2, 2, and 2 square root of 2. So when we unfold this again, let's see here, whoops. Now, that's 2 square root of 2, and the other side over here is 2 square root of 2. Alright, we're going to have to do some math here. Let me move it down here so we can see it. Cross it out. 2 square root of 2, 2 square root of 2. Let's do some math to figure out the missing side. And again, that's your right angle. And we're going to do a squared plus b squared equals c squared. So 2 square root of 2 squared. Now, if you're thinking, gosh, there's got to be an easier way. Yes, there probably is. There's other shortcuts, and that's what we sort of do. We play around with this math and sort of see what we can do. And sometimes the first way we try it is not the easiest way. There might have been an easier way to go about this. But let's do it just for a review, and we'll wrap this up. 2 square root of 2 squared, exponent rule says this applies to both. Okay, so what's going to happen is that's 2 squared, but 2 and squaring, so square root of 2 squared, and then plus. That's 2 squared, square root of 2 squared, and then still c squared. Okay. Alrighty. That's 4. This is 2. And so that whole thing just becomes an 8. So like I said, it's ugly, and these things are weird, and Pythagoras hated them. But don't worry about them, because when you square them, they just come back to whole numbers. That's what's kind of nice about them. They're weird. They're irrational, and then once you square them, they become rational again. Weird. Alright, so 2 squared is 4, square root of 2 squared is 2, equals c squared, and then we get, I'm jumping the gun here. I get 8. Total, we get 16. And that's not the answer. If c squared is 16, c is 4. So we'll wrap it up there. But like I said, this is important for a couple reasons. If you have a 45, 45, 90 each triangle, I can guarantee you're going to have the square root of 2 somewhere in there. It's not because my origami paper, we could have started with any number you wanted to. Square root of 2 will guaranteed come back in there every single time. No matter if I started with a 1 and 1 or a 5 and a 5, we'd end up with a square root of 2 in our problem. So that's what's kind of cool about it. Once you know this stuff, you'll see it more and more. So the more you do origami, you'll start noticing these patterns, noticing these 45s. And anytime once you see the 45, you know there's going to be a square root. And if you're building it out of wood and you don't want to measure square roots and stuff like that, well, then you got some other options. Or you make the whole number sides, and then the other 2 sides end up being the weird number sides. There's lots of things. You'll see them more and more. So thanks for watching. Keep doing origami, and you'll keep seeing math patterns, hopefully. All right. Have fun, you guys.